Welcome to Radio System Design, Module 4, Digital Modulation. So today we're going to be talking about the basics of digital modulation, including phase shift key and quadrature amplitude modulation. We'll also be talking about an important concept of symbol versus bits and talk about some basic modulation architectures. So the basic idea of digital modulation is that instead of using an analog time-varying envelope, we simply use a binary change of state. And so here's an example of amplitude shift key where we have one amplitude and then we have another amplitude. And we do this in discrete steps. And part of the reason to do this is that digital modulation can be more immune to noise. And the way to think about it is if I just have two different amplitudes, all I need to do is tell the difference between those two. I don't have to follow the fine variations of an analog one. So this would help if the variation in this envelope had some noise on it and this had some noise on it. As long as the separation was large enough, I could detect the two signals. So there's a couple different types of modulation. And all through this, we're going to be using a terminology called shift keying. And I'm not sure the historical origin of this, but I imagine it may go back to Morse code where you keyed in the code. And shift is just referring to what it is that we're changing. So on this top one here, it's a binary phase shift keying. And it's pretty easy to see that a 1 is this phase, and a 0 is a different phase. So all we're doing is changing phase as we move between 1 and a 0, meaning that 1 is a specific phase and 0 is another specific phase. We could also have binary amplitude shift key, which is like what we saw before. We have two different envelope amplitudes. One represents a 1, one represents a 0. And then of course we can have a binary frequency shift keying where we change a frequency between two. So in all of these you'll see this PSK, ASK, FSK. You'll just kind of see this terminology of something shift keying referring to what kind of modulation. Basically, as we talked in the modulation module, we discussed that you can modulate the amplitude, the phase, and the frequency, and so this gives you three different knobs to turn in a digital fashion. So I want to talk a little bit about the concept of a signal constellation. And we have two signals on the left here. One is A cosine omega t right here, and we have B cosine omega t. And maybe what we're going to do is we're going to go shift between A and B to represent, maybe this represents a 1 and this represents a 0. Well, it's going to be convenient if we do this graphically, and what we're going to do is we're going to take an axis, which I'm just going to call the cosine omega ct axis here, and this is basically showing that I've got one amplitude here and I've got the other amplitude here, and the constellation is basically going to go back and forth between these two. In this example it was cosine omega t. Often we'll just call this the in-phase component. And this will make a little bit more sense as we look at variations other than amplitude, because we can look at variations that might be caused by phase. And so here's an example where we have A cosine omega t and B cosine omega t, but we've changed the phase by 90 degrees. And so now we've basically moved up 90 degrees, and the amplitudes, if you look at this, is still different. So we can have this change between two amplitudes, and we can also have a change between two phases. So the way to look at this is you could actually, what I've drawn here is 4 different points, and we can actually continue this so that we represent signals on an in phase and a quadrature diagram. And so what we do is we plot basically the amplitudes and the phases of each signal that represents a piece of data. So in this example, this might represent 0 and this might represent 1. However, as we'll see going down, this could maybe be 0, 1, 1, or 0, 1, 0, and this could be 0, 1, 1. Each one of these points represents a state, and we can have a number of states. We can have 2, 4, 8, 16, as many states, frankly, as you want. And we'll see more of that as we go along. So let's look at an example. So this is binary phase shift key. So we saw this before. This is where we have 0 and 180. And we can represent this on the in phase axis as just a +1 and a -1. And so as we transmit back and forth, we just go back between these two dots. Another one is called QPSK, which is for Quadrature phase shift key. And you can see quadrature means I've got 4 different phases. And you can see here explicitly what I mean. Because there's 4 phases, I can represent 4 different binary numbers. Each one of these represents a point. So here we are with 180 degrees. Here we are with 0 degrees. Here we are with 90. And here we are with 270. And you notice the amplitude's not changing. I'm just changing the phase as I move between these different constellations. And this introduces subtly a concept of the fact that one physical state can represent many bits. Okay? We'll talk a little bit later, but we're going to call these symbols. So these are symbols, and they can represent a multi-bit state. Okay, and we'll talk more about that, but the basic idea is each one of these dots represents a piece of information. So this graph says that we can transmit 4 different pieces of information with one carrier frequency. Now, if we go back and we look at binary phase shift key, we can write it mathematically like the following. And what we have here, this is a string of square waves, and then it's going to be multiplied by a cosine of omega ct. Now, we've put in the phase in here, but if we choose the phase to be 0 or pi, we could just rewrite this signal like this. And the way we can think about this is this. The AK pi is my digital signal, 0101, and cosine is my carrier. And you can see here I've got my, let me erase that. I've got my change here, and then I've got, looks like it stays the same, and then another change there as we move along. And so here's our input information, and here is our cosine there. And so mathematically we represent it this way, and it's kind of convenient. If you want to know what this pi function looks like, it looks like this. It basically represents the minimum width of our pulse, and then we're just going to put on ones and zeros. So here we have a 1, here we have a 0, here we have a 1, here we have a 1, here we have a 0, and so forth. And so we represent our digital data as a series of unit parts of time where we assign them either a 1 or a 0. And as I said before, you can tell right here we've just got 2 bits of data. We've got 2 different states. We've got a one phase, and then we've got the other phase. And this leads us into this idea we've been talking about symbols. So this is actually an easy concept, but it gets complicated because down the road you're going to be hearing symbol bits, symbol bits, symbol bits, and it's going to be a little bit confusing, the difference between the two. And if you get them straight early on, it's pretty easy for you to be able to handle this. So the idea is that k bits can represent 2 to the k symbols. All right? And so the way to think about it is if I've just got 0 and 1, right? I have 2 symbols, -1 and 1. But if I've got 2 bits, meaning I can have 0, 0, 0, 1, 1, 0, 1, 1, I can represent this as 4 different symbols, right? And then I can go and I can say, well, if I've got 3 bits, I can do this with 8 symbols. And so the symbol represents the collection of bits that we are going to need. And so when we looked at our constellation where we have our I and our Q, each dot represents a symbol. It represents a collection of bits. And the reason why this distinction is important is we're going to transmit symbols in our digital radios, and each symbol can contain multiple bits. And so the idea is, I'll just show it examples here. Here's where we had this is 0 degrees and this is 180 degrees, right? And this is 90 degrees and 270, right? That means I can be coming along and suddenly shift phase, and I go from here to here. This might have been a 0, 0, and this might be 1, 0. So by doing one change in the physical domain from one symbol to the next, I've actually changed from those 2 bits to these 2 bits. And so it's a way for us to basically encode additional information by just sending one physical state and understanding that it can represent multiple bits. And we'll go over this in more detail, but this idea of symbols and bits is a very important one. And so let's take a look at another example here of Quadrature PSK. We looked at this last time. For binary PSK, the input, we chose 2 phases for each symbol, right? So we had a 1 and a 0 based upon the phase. And now for PSK or Quadrature PSK, and why do we say Quadrature and 4 PSK? And this is something that's important, is that I'll draw it over here. In a 4 PSK, we could have one angle here, one angle here, one angle here, and one angle here. And you can see this is just 4 angles, right? So you could call this a phase shift key, or we'll learn later you can also call this a quadrature amplitude shift key, because I have an amplitude here, an amplitude here, and an amplitude here. So 4 PSK can be referred to in a couple different ways, and we'll see about that in a little bit more. But let's look at what 4 PSK would look like in our waveform. And so you can see down here, as I mentioned, each symbol, each physical state that we transmit is a collection of bits. In this case, because there's 4 states, it's 2 bits. And an important thing to understand with this is that the bandwidth of the signal is related to the time, the period of the symbol that we transmit. And so the bandwidth of the signal is related to, or the time is 1 over the bandwidth, and the bandwidth is related to 1 over the time, which will become important in just a moment. And you can see here, as I mentioned before, we're sending twice as much data. So I think a really good example to look at is in 4 PSK, I'm transmitting this signal that's 180 degrees of phase, and you get 2 bits, you get a 1, 1. In BPSK, I transmit the exact same physical signal, but it only represents 1 bit. And that's because my receiver knows that I'm traveling either QPSK or BPSK. But you can start to see how I can transmit a signal, and with higher order constellations, it's actually going to transmit more and more information. And like I said, this will become more clear as we move through higher orders. And so here's another view for Quadrature PSK. We can write a 4 PSK or Quadrature PSK as similar as we've done before, and now we've got 4 different phases. And we just play the same trick that we did. We're going to convert this phase into a pre-factor, and then we can just split this up mathematically. And if you're wondering, how did I go from this step to this step, you remember in class cosine of u plus v gave us a cosine of u cosine of v minus sine of u sine of v. It's just a trig identity. And then here we can just move this summation right here, and now we've got 2 signals that are right here. And if you choose these values for your phase, we know what the cosine phi of k will be and sine phi of k will be for each. And then we can actually write QPSK as this top version and this bottom version. And you can see that that's just simply a BPSK signal and a BPSK signal. And the reason we're able to do this is we basically are transmitting two BPSK signals, but they're orthogonal. One's cosine and one's sine, and if you remember from the analog modulation lab, we're able to transmit orthogonal signals without disrupting one another. All right, let's look at how we might implement a quadrature modulator. So a 4 PSK signal could be seen as the sum of two BPSKs and can be generated by a quadrature modulator like we saw last time. So here's one BPSK signal, here's another signal, and we just transmit them using quadrature signals, which we learned in the previous module. And what happens is, actually in the digital domain, we've got our large series of data we want to transmit, and we put it into a, actually it's a symbol separator. It basically takes this data and puts all the, every other bit there, and then our quadrature modulator transmits those just like we'd seen before. And as I said, the incoming data is divided up and then modulated with cosine and sine. We call this data I call it I for in phase, and this one Q for quadrature. And likewise, this is the in phase component of the signal. This is the quadrature component of the signal, as we talked about in analog modulation. So there's some important questions here. The two signals which we just added have different data, right? This is different data than that data. But they have the same bandwidth and they have the same transmit frequency. So once again, how do we transmit both of them? And just remember that it's because we have orthogonal carriers that we're able to transmit each one of these. Okay, so this is how simple quadrature 4 PSK would work. Let's look at some other different architectures that'll give you a little bit better idea about how digital modulation can work. So looking at higher order PSK, you can extend this pretty much at will. So here's QPSK. Here is 8 PSK, so there's 8 phase shift. And what you can see is we're just adding more and more phases. And we can keep on going to 32. One thing to notice that's changing here is that the distance, right, between 2 points gets smaller and smaller. So it's not like adding more steps comes for free. The space between each symbol actually gets smaller. And if you're wondering, well, why does that matter? Well, you probably can think that any physical system isn't going to be quite perfect, and these dots will actually be little fuzzy balls just due to noise in the channel. And as our signal gets weaker and weaker and weaker, we can put an amplifier on it, but these will actually get larger and larger and larger, and you can see that if the noise on one symbol and the noise on the other symbol overlap, I can't tell the difference between the two. And so the noise immunity becomes worse as we increase the number of symbols in each digital modulation scheme. And so one basic way to think about this is that the more data you're trying to send, the more signal power is needed. Because remember, the bandwidth of what we're transmitting is always the same, because the period, if you will, this period of our symbol rate, the symbol is one of these dots, and here in 16 PSK it is going to be 0110. It's going to be 4 digits to give us a total of 16 possible points. And this period t has a rough bandwidth of 1 over t. So as we increase our complexity, since we're transmitting each symbol at the same rate, the bandwidth stays the same, but we're transmitting more data because we have more bits, because each one of these, we now have 16 different levels to transmit. But the problem is that we have less noise immunity, and the only way to fight that is to increase our signal power. So let's talk about quadrature amplitude modulation, or QAM. This is probably the most popular type of modulation for higher order modulation. And so an effective solution for increasing the bandwidth efficiency is to combine both an amplitude and a phase modulation. And what I've done is I've shown you an example of 16 QAM here, where here's the in phase and here's the quadrature. And what you can see is that we've gotten two different values of amplitude, right, for both the in phase and the quadrature. And a way to also think about it is I've got an angle here, I've got an angle here, and I've got an angle here. So you can think about it as a magnitude and an angle, or you can think about it as simply superposition of the I and the Q. And what we're really concerned about when we do these higher order modulations is two aspects. One is the power, and the other one has to do with the noise immunity. And the easiest way to compare different combinations of amplitudes and phases is to look at this constellation diagram like I've shown you. And I'll show you an example here. We can do many different constellations. The key things, as I mentioned, is the minimum distance between symbols. And so that's shown here in the red. And once again, that's because as I get noise on this point and noise on that point, the more noise I have, the closer they'll come to one another. So if these two are far apart, I can have a lot more noise and still detect my signals. And the other one is the power. And basically the maximum distance, this blue line, is the power of your signal. And the way to think about that simply is, at this point, I have the highest I and the highest Q amplitude. So I have the highest I power and the highest Q power. And as I go further out, these are going to have higher amplitudes of both, and therefore the overall power is going to be larger. And there's some other constraints that we may need to look at for the generation of I and Qs that may make some constellations preferred over the others. And a good way to kind of summarize this and understand it is to look at the contrast between 16 PSK, or phase shift key, and 16 QAM. And the key differences you can see here are that while you could set this up for the same distance, so let's say that red is the same distance. And if you're saying, well, how would I do that? Well, it's pretty simple. I can just make this circle bigger and bigger and bigger, right? Until this distance exactly equals that distance. And so our noise immunity between the two would be exactly the same. But if you run through the math, it turns out that this amplitude here, to get this separation, is 1.6 dB less power in QAM than it is in 16 PSK. And that basically has to do with the fact that the distance between any 2 points here is the same as in 16 PSK, but the peak to get to the corner is smaller than this peak. So here's a great example where they both have the same bandwidth because we're transmitting at the same period t. Right? They're both transmitting for each one of these 4 bits. They both have the same noise immunity. Okay? However, this requires more power. Okay, so it's clear to see that our constellation choice really does have some trade-offs between the different types. Why might you pick 16 PSK? Let's just do an example. Maybe the hardware that you're building, you can change the phase easily, but you can't change the amplitude. This is actually very true in high frequencies, so tens to maybe 100 gigahertz or more. You want to have your amplifiers always at a fixed amplitude. You never want to have them change amplitude because they become very inefficient. Therefore, it's better just to change the phase. So in those systems, this one, the 16 PSK, would be more attractive. So it's not that one is better than the other, it's just that you need to understand the trade-offs. And at this point, you shouldn't understand all the trade-offs, but you should sort of see the key concepts of noise immunity and of power and of the fact that they're all the same bandwidth. I want to take one final minute to talk about what these constellation diagrams look like. And so down here on the left is a simulated version of a 16 QAM, meaning there's 16 points. And up here, these are actually the, I may not get these, it doesn't matter if they get reversed. So here is your, your quadrature, and the blue is your in phase. And so what this means is that the in phase, which is blue, is going between this value, this value, this value, and this value. And you can see that I've got one value here, one value here, one value here, one value here. They correspond to these values that I just showed. Likewise, the pink has one value, two value, three values, four values, and I've got 1, 2, 3, 4. So the actual waveforms that we look at going into our transmitter have these multi-levels. And if we're to plot each point here, we would get a dot corresponding to each one of these 16 different states. However, as you can see, they transition between, and so oftentimes the cartoons look like this, and we just see the points, but in reality, if you looked on an oscilloscope, you would see it like this, where you're seeing the transition between points, where each one of these is one of the points that we saw over in this diagram here. This is nice and clean because these are square. In the next lab, or the next module, we'll learn a little bit about pulse filtering that actually makes this not square and makes these experimental measurements of the constellations a little harder to read. But you should at least now be able to translate between the pictures you see in the cartoons, what you would see in an oscilloscope, and what the actual I and Q waveforms would look like. All right, that's the end of the introduction for digital modulation. We talked about phase shift keying, quadrature amplitude modulation. We talked about the important concept of a symbol and a bit, and that symbols can contain many bits. Remember, I'll just do this as a quick overview. A symbol is one of these dots on the constellations. And each dot, in this example I'm doing a 16 QAM, each dot represents 4 bits, and we transmit a symbol per period. So for each period t, we transmit 1 symbol. In 16 QAM, that means we transmit 4 bits. So this is how we're able to increase the information we send by making these constellations bigger and bigger and bigger. We keep our bandwidth the same because our period is the same. We increase the number of symbols, and each symbol contains more bits in it. And we also looked at a basic digital architecture scenario.